Hey, this is Dr. Liu. This is a data analysis video for the Projectile Motion Lab. So I have two data sets. The left side is the speeds, the right side has some distances from a past time. It wasn't exactly for this semester, but I have some data I can show you how to analyze. So this is what I did with the angled and horizontal launch. So I have 0 degrees and 30 and 60. You'll have different angles except that 0 is always there. And instead of 5, I launched 10 times, which is I'm trying to see if that makes any difference. And it seems like it makes a minimal difference. So you're only required to launch 5 times. But this side is to get the average and standard deviation speeds. So let's have a look at what we are supposed to find out. So here I have so 5 sample averages. Basically, I just took the first 5 samples, and also I calculated standard deviation. And that's for all the 3 angles. And the number of sig figs should be this way. So this number used to be um, like this. All right, so that's Excel doesn't really know what we want. This is a standard deviation, so it is an uncertainty field. So it should only have one sig fig, the leading sig fig should be the only one that we keep. And then we see that the sig fig is the second number after decimal. So that will line up the average, which also had a lot of digits. So we line it up so that the standard deviation will line up with the number of sig figs after decimal for the average. So 4.79 plus minus 0.03, not 4791234 plus 0.01, 0.03. So this is how you would do it. Otherwise, you would get some points docked. So make sure you have the right amount of sig figs. And that works for all three. So I have the standard deviations and the averages. So what I want to do is I want to see if all three speeds are essentially the same speeds in with my uncertainty. What this means is if I compare the first and second speed, are they within the same? Do they actually overlap? If I apply this 0.03, so let me apply the 0.03. I'll redo this. Those are actually 10 sample averages. So I may as well just hide them now. Let's do that. And upper and lower is just this. So I just take the average and plus standard deviation. I'll do that for all three. Lower is average minus standard deviation. So this gives us a range. Okay. Okay, so this gives us a range. So the idea is, does this range overlap with this range? If it does, that means the two numbers are, well, sort of the same because they overlap with their uncertainty. So do they overlap? They actually do. So the low is 7.6. The high is on this other one 7.7. So they overlap very minimally. So within the uncertainty, these two numbers can be considered about the same. But if you look at this other angle here, okay, these two do not overlap anymore. They're just on the border, and these two sets definitely don't overlap. So the lowest this number could be is 7.6. The highest this other number could be is 7.0. So within the one standard deviation, these two numbers are different. What this means is our speeds are gradually changing at different angles. You can see there's a trend of decreasing speed. Now, later you'll learn about energy conservation. Gravity does some negative work if you shoot at an angle, so the speeds will be less. So that is expected. And I just showed that um, the values are not supposed to be shared at all different angles, such as if you do a 0 degree angle launch, you get the speed and you can pretend that was the same speed at any angle, and that is incorrect. So I want you to be able to draw that conclusion. So that's this part of the result, and you'll be using these two speeds also for prediction. Okay, so let's look at the launch width distances. So you're not required to collect the speed data anymore when you're launching at an angle. I don't have a 30-degree angle launch, but I do have 38. 30 is not too bad, right? So if you had a 30, that means that you'll be able to use that exact speed for prediction. So with my 38, I measured all the 10 dots, the distances, and also I did an average and also did a standard deviation. Because the dots were spread, they were spread out, even though I was able to get maybe up to a couple millimeters accuracy to each dot, the spread of the dot gave me about a centimeter accuracy. So see, this is when the average is actually less accurate than each individual value because there is um, this spread. So I have that distance. And I also have launch angle. In case you forgot to measure, you can take my launch, not launch angle, launch height. You can take my launch height. This is very, um, well, accurate down to about a centimeter because the benches are the same height. And that was my angle, and I converted it into readings. In the previous video with old data, I already did all this. So let's just do this here. I had mm, let's see, this one I had a 4.87, even though that angle was different. So I used that speed. Okay, so this speed you'll be getting from your actual angle launch, and you can calculate the launch time. This is a formula for. I had an 8 here. That was an older. Let's see. Can I double click into it? I don't know. Doesn't really allow me to add it. Yeah, not sure. Guess it doesn't really want me to add it. Okay, this is equation 4. So you put your speed. Um, This is speed y, so you do speed times sine of the angle, and that's the height. Everything has to be in meters, meter per second, and you calculate the launch time. So you'll get something close to about 0.9 seconds. And then you can calculate distance with this equation, which in our case is equation number 5. So you'll be able to get that V0x is V0 cosine. Let's make sure you don't just do V0. So that'll give you the expected distance. And the relative uncertainty will be the measured results, right? So you have standard deviation, you have average. So standard deviation over average is the relative uncertainty. So this is how accurately you were able to measure. You were able to measure it down to about 0.3%. And there's also relative error, which compares your number with a prediction. Okay, that's a bit far. As we know, our speed is probably not this high because as we angle the launch, the speed actually gets a little less. Um, a couple percent, but in the correct direction. So we may be able to prove this, even though my numbers didn't prove. Okay, remember, you have two different angles you want to prove. And you will have two copies of all these in order to calculate. Maybe here's a copy, here's another copy paste, get different numbers in, and make sure you have the different launch speeds, and hopefully all those calculations are linked to the numbers in the cells, and you'll be able to get everything out. So hopefully you can prove it, the relative uncertainty bigger than relative error.